our work is usually on quantum chemistry related research with machine learning, but I will show later. So I had before postdoc Arifullah, so he was working on quantum dynamics, and he's still working, and we collaborating on this. But my major topic is nanoabatic dynamics, which I will highlight here, right? So I saw also this nice Google Doc set up by Alexei. So he shared with participants, and there are many issues which repeat, kind of. So it means they are very important for the community, right? Like uncertainty assessment, I think. Uncertainty measurement, so it repeats many times, and then related to it, like sampling, how do you sample points, again, uncertainty quantifications many times. So I think it's something which is very important, and then how to enhance sampling of conical intersections. So these are all problems which we worried about, and in this community struggle with them, right? And of course, we also worry about them, we struggle with them, and I hope that today I can show you some of the solutions, latest basically research from our group. And I would even go so far to say that we struggled 8 years with this, and finally we got something which I am more or less happy about after 8 years. So we just put the preprint out there. So I was not happy with many of our previous models. That's why we didn't publish many papers on this topic, because I wanted to get something which works kind of easy enough. So now we've got something which works easy enough. So within days, you can get precise machine learning nanoabatic molecular dynamics results on a single GPU plus 16 CPU threads. And basically the whole topic of this presentation will be explaining how we achieve this. So that's a bit complex workflow, but all of these components were necessary to achieve this. And before I jump into that, I need to explain who was doing the job. It was again 8 years, so many generations of postdocs and students. Not everyone survived, many graduated. So it means it's really lots of effort. And like here, John Lina, so she was PhD student for 4 years, and graduating soon, hopefully. So she was trying to do this active learning and struggled a lot. And now Mikolai joined last year as a co-supervised PhD student. So he will actually give you a short demonstration at the end of the talk. So I will pass the torch to him later. And he managed to finalize this into this coherent workflow. And he's co-supervised with Jan Jankowski in Warsaw University. And most of this research is driven by our goal to make AI-enhanced computational chemistry simulations and workflows in general. Machine learning and IMD is a part of it. But it really stimulates all these workflows. And this is done by many people, as I mentioned, in collaboration with also many people, especially Mario Barbati, as I will explain later. And we also have a bit of machine learning quantum dynamics research, but that was brought to my group by Arifullah, and he's now independently in other university. So if you want to learn about that, you would need to listen to him. I would just mention a couple of these showcases of his work on quantum dynamics, that we have the struggles to do this propagation fast because it's computationally expensive with normal HVM equations or other equations. And Alexei is in the audience, so Arif was inspired by his work, and he come to me and say, I want to do something like this. I said, okay, try to do this. So he was doing this with kernel methods instead of neural networks. And at the end, we'll collaborate it with Alexei, because what is then the better methods, the kernel methods, LSTM, and many other things around. So we benchmark them. So Alexei probably also will talk about this, maybe not, but anyway, so we've done this work. We've figured out that simple models actually work better than more complex models, at least for some cases. And I will not talk much about that. I'm just showing like these highlights. And another thing is that we learned that, okay, you can do it recursively, but that's the same way as doing HEM, more or less. So what we suggested to do is also learn dynamics as a function of time directly. So propagate, like just predict trajectory as a function of time. That's what we want to do anyway. That has many benefits because it's smooth function. It's not depending on discrete steps and so on. So we showed it's possible for FMO complex. So we got very decent agreements to the reference dynamics. And later, Arif, actually, before I go to the next example, I tell that we managed to do it also for molecular dynamics here for ground state. In terms of, here you see that we predicted nuclear configuration as a function of time and initial conditions. That's stable for more than 1 nanosecond, very fast, and works for different molecules. But then Arif has this also very nice idea that, okay, why not predict the whole trajectory in one shot, right? So that's also possible because neural networks have multi-output feature. So that is also possible to do with machine learning. We show then you can predict this 10 picosecond long dynamics in just 70 milliseconds. Very fast, very efficient. But with this, I would basically finish all my quantum dynamics prelude to the real topic of this presentation, which is back to going to nanobatic dynamics. And for nanobatic dynamics, we struggled a lot for 8 years. And that inspired lots of these computational chemistry simulations and workflows too, which is the usual topic of my presentations. And so that's why, as a chemist, I got into physics a lot, and now I am kind of in both departments, in chemistry department and physics departments in different universities. So that was really big inspiration for us. So after this kind of quantum dynamics, when I talk about nanobatic dynamics, I'm talking mostly about trajectory surface hopping. And that was done because Mario Barbati came to me like 8 years ago. He organized a conference, and then we knew each other from our like Max Planck Institute time. And then I was doing this machine learning, and he says, "Oh, it would be great to accelerate this surface hopping dynamics because even like modest simulations shown here, like 100 trajectories, you propagate 0.5 time step, it amounts to like 200,000 calculations, right? Even with this modest." And here I don't need to explain to you, but basically we are trying to make it more practical, which is easier and not just faster to propagate trajectories, because of course, when you have a machine learning model, it is faster. But how to make the whole workflow easy and reasonable. So that's the biggest problem. And that's definitely not easy. We had some proof of concept showing that, okay, in 2018, 6 years ago, we showed that, well, it's possible to do for this kind of test spin boson Hamiltonian system with 1,000 to 10,000 points, and still we needed some tricks to do it properly. So it was even not pure machine learning dynamics. But at least why we were testing 1,000 and 10,000, because our vision was that for a good machine learning model, we need to get to this number of points because ground state dynamics work with this number of points, right? So what's the problem with excited states? Of course, they're more complicated and so on, but still, there is potential to go down to like maybe preferably at most 10,000 points, right? So if you can get nanobatic dynamics with 10,000 points and sampled fast and efficiently, that would be our ultimate goal. And that's something we set back then, and only I would say now we can achieve it. And here is one example which I will come back to, but just showing that, okay, this is example for simple systems. We can already achieve this, like this Fulvin. This is like population dynamics, and with less than 6,000 points, we get quite decent population, right? Compared to the reference CAS-STF. And now the whole talk I will be explaining how we've done this. It also works for larger systems with even less points. funnily enough, and photoisomerization reactions like 6,000 points. So it does work. Again, I will come back to this, but basically just a bit of spoilers that it's done with this workflow. So the workflow is based on active learning, and that's the obvious way that the community is trying to do, right? And this active learning consists of kind of seemingly simple idea and loop. So you need initial data, you label them with some reference method, you have machine learning potentials, then you do some propagation of dynamics, basically. You sample points, check whether it's converged, and then you get the final machine learning potential, right? But each of these steps is highly non-trivial and needs methods and software. And that's why it took 8 years to develop all of this. And this non-adiabatic dynamics was really one of the main driving forces in the development of the Emulatom package, which we used to implement this workflow. And so in this package, we basically combine both machine learning, quantum chemistry interfaces with different simulations, data handling, and so on. And it was all essential to make it work in an efficient way. And for example, when we talk about labeling points, so you need some interfaces to quantum chemical software, quantum chemical methods, and then of course you have different choices, and we have ab initio, like for excited states, particularly ADC2, KSSTF, many other methods. Like for semi-empirical, we have these different implementations provided by MNDO program, OMX methods and ODM2 methods, and so on from Baltatil. And then we have some of our hybrid machine learning quantum mechanical methods, and then we have some pure machine learning models, and which are already useful for the next step when we train machine learning potentials. And as you see, they're all for us actually considered just models, because Emulatom doesn't differentiate between them when they're used in simulations. Of course, machine learning models can be trained, so that's a new feature of these models, or a different feature of these models. But in Emulatoms themselves, they are kind of all part of a big family of models that are seamlessly used in different simulations. And of course, we have this traditional scheme coming from semi-empirical methods to DFT and like wave function-based ab initio methods. And now with machine learning, we can either completely substitute them by building surrogate machine learning models, or we can combine them with different like DFT or semi-empirical methods, wave function-based methods to improve them. At the end, we also have universal models, but that's not part of this talk. So if you're interested, you can check out my website. But the major method now is UA-IKM, which is provides also tries to provide couple cluster accuracy for ground state properties out of the box and at this kind of speed, so semi-empirical DFT or pure machine learning. So now the next stage is, of course, we need to do simulations to sample points, but in general, you want to get some results. And for simulations, also we implemented in one package those different calculations from geometry optimizations like frequencies or normal mode. Sampling can be also done here, and then molecular dynamics and different spectroscopy. For our excited state stories, the most interesting part is surface hopping dynamics. So it's also there. And the whole workflow, like for geometry optimizations to getting the final populations, can be done in dozens of lines in Python using Emulatom. And again, with different models here. So that's all allows all this flexibility in what we could try. And that was essential to test, like perform thousands of different experiments with different models, with different settings for active learning, for different settings also for how we train the models and so on, right? How we sample uncertainties. And then we come up with the final protocol after 8 years. And this package, so this surface hopping can be, so we tested, for example, using this AIKM1 method, which is delta learning method, and using AIKM1 model. here, and it produces some decent agreement with experiment for quantum yields of this cis trans-isomerization. So that was Mikolai's idea to get benchmark for this one. And as mentioned before, this one is very good for ground state for us. That's couple cluster accuracy, CCSD parentheses T, at semi-empirical level cost. While this method is good, we still, again, want to do simulations, and then in this active learning loop, just doing surface hopping simulation apparently was not enough. So one of the biggest problems was we realized the description of gaps is the key. So in all of these procedures, all this active learning really needs to sample small gap region. So that was really the biggest problem. And that's why we come up with this new protocol. So then we run just CapMD, and I come back to this, but we sample this region with small band, with small gap, energy gap, and this allows us basically to map the region near the conical intersections. And so after these, there are many other questions. How do you get the points which are sampled? So here is converged, so it's a bit also misleading. I should have put also sampling and convergent, right? Because if you do simulations, you need to sample. But how do you sample? How do you judge whether it's converged? It's also crucial. There are many choices how to do this, and we tried also many. You can believe us. So the problem is here that there are many also ways to judge. Like so, this uncertainty was I highlighted in these Google Docs was one of the most frequent keywords, right? So people really think about how to judge uncertainty. This is a big problem. So we suggested actually a bit different approach. So people use usually query by committee approach. So use ensemble of neural networks or other methods, and then they look at the deviation between neural networks. And the question is how you see you generate these different neural networks, and there are also many different approaches. And this approach works decently, like for many applications, because there is enough evidence in literature. We were thinking that there is still too much kind of subjectivity into this, but we actually have very nice and simple way to judge uncertainty from the physical perspective. So as a quantum chemist, we know, or let's put it this way. So as a quantum chemist and machine learning person, we know that if you have infinite number of points on potential energy surface and know all of them, machine learning model can learn them, and then it will perfectly reproduce potential energy surface, right? So the problem is then if you don't know some points, then it will start guessing this. And it will be guessing better if you have gradients, but it still will be the guess. So that's the key point. So when you put gradients, accuracy improves, but that's still a guess. If you don't have a point here, it still doesn't know what is the energy. It can be very different, because here in this vicinity of training point, probably this gradient can give you quite good guess, right? But it can be quite abrupt change in the shape of the potential energy surface, particularly when we talk about excited states. And when you have this abrupt change, well, then you just don't know it until you sample this point. So the key is how do we know and how to sample this point? And our idea is very simple. So basically we say, you need to sample it by checking whether you have enough information on the from geometries in your training data to deduce this like whether the accuracy here is good. And here we basically compare whether, given this more physical information force, so from which you can extrapolate a bit better, whether it deviates from the model just straight on energies, which has no additional information, because the energies only model knows really the shape only from these points, right? So it has no additional information. So that's super simple idea, but it's very robust way to judge uncertainty, because if you just don't have points, it will deviate. There is no, I mean, it very in rare cases, I can imagine it can accidentally give similar result, but in principle, if you as the farther you go away from training points, it will start deviate like crazy. So this approach is super robust, and then it produces, give you very good uncertainty estimates whether it's good or bad. And it's super simple to implement because you have just main machine learning model trained on forces because it's more accurate. So you don't have many models to train. You just have one model to train. It's fast to train. It's also fast to propagate because you just use one model to propagate. And the only one additional, this auxiliary machine learning model, well, it's super fast to train because it's just trained on energies. And then you can throw away it. You don't need to propagate dynamics with it. You just check uncertainties. And once you found this deviation, you add it to the training data, and then your models both improve, and then you do simulations and repeat this procedure. So super simple idea, but we were the first to kind of come up with it. So that's very nice. And that's very robust way to do it. But the question is, how do you choose what is a large enough deviation? And then people start guessing like, okay, let's put 0.09 harder for whatever reason, because we'll start with this and then we can reduce it later by hand, right? It's a reasonable also approach because, well, then you get some result and then you have, from your like human like expert, as a human expert, what kind of errors you would need to get it right? We come out from it, okay, we don't really want to, from human, many inputs. So we want to make it as physically and statistics based as possible. So we don't want to ask users to give thresholds. So we want to get thresholds determined from statistical point of view. And what would be statistically reasonable thresholds? Well, our suggestion is very simple. If we have some initial data set, which I come up later, then basically what we want to have is that in 99 at least percent of simulations, when we run these simulations, right? So for this data set, which we have 99% are confident. Otherwise, we'll need to sample, so the simulations will break down like more than 1%. We don't want to do that. So we want that our simulations is basically 99% for the given distribution of the data, so from which we train the model, is stable. And then when we hit some models which have uncertainty higher than this, then of course we have to sample them, right? But when we have already some data sets, some distributions, so we don't want that more than 1% is uncertain. So that's pretty simple statistical idea, practical one. Now we need to know what is our initial data set, and that's another good question, right? For initial data set, practical decision is to do the same as we do in non-adiabatic dynamics, so, well, Wigner sampling, right? But then from Wigner sampling, how many points do we need? So that's the question. And when we think about how many points we need, that's already another statistical law gives us a solution. So we know that the error of the model drops fast when you add training points at the very beginning, but that starts dropping very slow. So then basically after some point, it doesn't make any sense to add 10 times more points just to squeeze out, I don't know, 5% improvement in accuracy. So it doesn't make any sense. So you just cut it there and then you stop adding more points to the initial data set, and that's enough. So those are our statistical considerations. Then you don't need to decide about initial data set, and you don't need to decide about uncertainty quantification anymore. Then you put it in the loop and then it runs. So we tested it for ground state. It works nicely. So we get nice vibrational spectra with less than 1,000 training points with Zani potential, with very small error on the test trajectory, 0.1 kcal per mole. So that works. Then for it, this procedure identifies on-conformers of glycine. So it can detect all these different conformational flexibility. So that also works. It also works for reactions and quite big systems like fullerene and this one. So we discovered some ray events like roaming and so on. But coming back to excited states is, does it work for non-adiabatic dynamics, right? And the answer is, well, in this way, still not. That's why we need many more things to make it work for non-adiabatic dynamics. And for non-adiabatic dynamics, here I start to decipher a bit this scheme. Basically, what we need is machine learning potential. And for machine learning potential, well, there are many of them. We tested many of them too, believe us. And surprisingly, some of them fail very badly. Also, one of our methods. So that's why we switched to neural network honey. We tested them, equivariant ones also tested. I show some results preliminary. That got kind of good recognition, but the problem is there are, for excited states, we really cannot, well, we can apply them, but then they will be like single state models, right? That's not very good. Also from efficiency point of view, but also you don't learn properties between states. There are also multi-output models in literature, so they're not our inventions. So Schnark and other models, they also can do this to very good extent, but accuracy is usually in terms of RMSE less than for single state. Now, our suggestion is to use multi-state models, which also very simple idea. You just put the state number in the input descriptor, and then you get your excited state property based on your input. And this gives very, very nice results for energies, excitation energies for like even 8 states. So we can learn arbitrary number of states. There is no limit, right? So that's very nice. And then this multi-state model gives errors, which even for high excited states are lower sometimes, or for like much lower for lower excited states than single state, like any normal any model which you would train on ground state properties. So it actually improves, even for ground states and excited states improve when you add this information from different excited states. So it really improves a lot. And after this, so we have this new model, which is much better for this, but we also know that these low energy, low small gap regions are very, very important. So we added this loss to this gap, and that allows us to improve also error. So reduce the error for the gaps between the surfaces. So that's also very important. And finally, we know that just benchmarking, just showing these test RMSEs is not enough. So test RMSE is not equal to the simulation quality. So we do need to do it in the surface hopping dynamics, and it would still probably not work because we tried many times with single state models to be more precise, but also with different multi-state models. It wouldn't work well unless we sample points in this small gap region. And what we do here, a bit alluded to it, but basically when you run on one surface, you need to, you can go very fast to the larger gap region, and then it will not sample enough here points, right? So you would need to run many, many active learning iterations to make it work without gap dynamics. So with our gap dynamics, what we do is basically we switch to the forces, which are difference between forces from upper surface and lower surface. So very simple. And when you propagate these dynamics on this kind of, with this gap for forces, then it will return. So the dynamics will return back to the small energy region, small gap region. And then it will sample more and more near the conical intersection. So that was essential to make fast improvement and fast active learning. Then also we done this, so we need, it's a bit more complicated than that because we need to switch back and forth, so adiabatic and gap forces depending on energy gap, but probably I will skip a bit because I think I'm already too slow for this. And then we need to sample, and sampling is also not that simple. So uncertainty, yes, important. So we do this using uncertainty for the current surface, but we also check uncertainties for up and down surface using our criteria from before for ground state. We also check whether our machine learning model produces negative gaps, because that's an indication that something is wrong, right? So you cannot have negative gap. So it means that we have some problem with the training data. So we sample these points too. So this is basically our workflow for sampling from trajectories. We check uncertainties for each for surfaces, current surface up and down, and for sample points with negative gap. And then one additional thing which we do is sample based on hopping probability, right? Because we can look directly at what so to make propagations or population stable in active learning, very often what we see actually, and many people maybe can confirm here, who tried any active learning, that you do active learning, some iterations look very good population, and the next iteration it becomes very bad. So the problem is that we never look at how uncertain are hopping probabilities, right? So if you look at the uncertainty in hopping probabilities, then we know, and if you have very good, accurate hopping probabilities, then populations should be also okay, right? So that's why we look at how uncertain our hoppings. And we do this by basically using this very simple, or at least approximate, maybe it's not very simple, but approximate Landau-Zino-Belayev-Lebediev formulation, which we also calculate in this trajectory surface hopping. So we use the same equation to calculate hopping probability with our main model and auxiliary model. And then we check whether it exceeds some threshold, and then we add these points to our data set. So this basically summarizes all our kind of procedure. And then we've got like with less than 6,000 points with 3 days on a single GPU and 16 CPU cards for the whole procedure, active learning procedure, it was done. And this population was done. Now with single state models, it was doable, but with 15,000 points in like more than, I don't know, 30 days or more. So it was really slow. Now population hopping distribution is good. And we also tried Maze, which is a covariant neural network, very nice model. Everything is good. The problem is it takes much longer, 28 days, and then it crashed due to some memories, and we give up. So then for big system, it also works. As I showed you before, for photoisomerization, it also works nicely for this other benzene, for both like directions, trans, and cis trans. So these are really machine learning trajectories. So I'm showing you machine learning trajectories. And then the very nice thing is that this one model, we trained one model which works across systems because, well, it can learn this. So we trained one model, so it gives us really hope that we can have one model which can work for many systems. And finally, basically summarizing this, that we have these different uncertainties. We touched upon many of these topics. We even know that now, okay, we use local model, which also works for excited states, at least for these kind of systems. But I can imagine that if we have some charges and so on, electrostatics should be important. But then usually our delta learning models kind of work for that. And finally, I would say that, okay, we plan to release this next Wednesday. So Mikola is working now very hard to making this release. But you already can try the new features on Lion's xCloud. And basically, I will stop here and give Mikola to show you maybe how to do this.
Okay. So the first tutorial will be on using the multi-state ANI model in MLATOM. By the way, all of those tutorials are done on the Zax Cloud in the Jupyter Lab, which is free to use. So the first thing we have to do to use the multi-state ANI model is to import MLATOM as a Python package, and then we can define a multi-state ANI model just as a normal Python object called model here. And then, of course, we need some training data. And training data here is loaded as a MLATOM molecular database object that I have prepared beforehand. This is a small data set that will be used here for demonstrational purposes. And then training the model is just as simple as using the model.train method, where we pass the molecular database, name the property to learn as energy, and the derivative property as energy gradients. And here I'm also cutting the maximum number of epochs to only 100, so it finishes relatively fast. And okay, we can run this cell, and we see that the model is training. Okay, maybe and the model file here with the name Fulvene tutorial, as I named it here, is created. Okay, so once we train the model, and this will be done very soon. We have to wait for 100 epochs here. We can use it to make single point predictions. And for that, we need a molecule, which is again defined as a MLATOM data molecule object, which we can read from a simple XYZ file. And using the newly implemented feature view, we can even view it directly in the Jupyter notebook. So here we have a Fulvene molecule. And we can use the model.predict method to make predictions for this molecule. And then we print out the energies of the ground state, the first excited state, and the energy gap between the two states. And finally, we can also use this multi-state ANI model to run NAMD directly here from the Jupyter notebook. And for that, I will load the ANI model that was trained in the active learning group, so we get some more reasonable predictions. And also we will need an initial conditions database and all the NAMD arguments, such as the model that we will use, the time step, maximum propagation time, hopping algorithm, number of states, and etc. So we do that, and then we can run simulations in parallel using the ml.simulations run in parallel wrapper. So I run that, and this should take about 30 seconds to a minute to run for trajectories. So for this method, you just need to pass the molecular database that you want to use. So here I pass only the first 4 entries of it, the task, which is surface hopping MD, the arguments defined here, and this method will take care of the parallelization of your simulations without any problem. So this is done, and then we can plot the results using also MLATOM without any additional software. And we see some plot of some population plot from NAMD. And additionally, those trajectories can be analyzed and visualized using very simple Python code. And an example is shown below, where we look at the energies and the ground state and the excited state energies during the simulations. Also, very quickly, I have another tutorial here for GapMD. This should be even faster. Again, everything is implemented in the Zax version of MLATOM. And starting from some initial conditions that we load, we again define a model, and then GapMD can be run using ml.gapmd, where we pass all the arguments such as the maximum propagation times and the lower and upper state between which the GapMD will be propagated. So once we run that, this is very fast. We can view the gap dynamics trajectory. And here we can see that the molecule is actually exploring the vicinity of the conical intersection. When we look at the angle between the 5-membered ring and the CH2 moiety here, it forms about 90 degrees, which is characteristic for an heteronic type conical intersection. Okay, so maybe for the sake of time, I will finish here, and thank you very much for your attention.
Active Learning Protocol for Surface Hopping Dynamics was presented for the first time at the MolCI workshop Machine Learning in Quantum and Non-Adiabatic Dynamics in 2024. We thank the organizers for allowing us to share the presentation video here. All original videos you can find at the link. The protocol is now available in open source MLATOM with tutorials as described on GitHub.